Hello everyone. Today we are starting our new subject of solid state pharmaceutics, that is PE660. We will be studying various topics in this particular coursework, including the introductory part, which we are going to take today. And then subsequently we are going to move to the crystalline state, amorphous state, co-crystals, and the regulatory aspects of solid state characterization. As the name indicates, solid-state pharmaceutics is comprising of two words, solid state and pharmaceutics. Solid state, as we know, is the compressed state of matter, wherein the molecules of the compound are held together by strong intermolecular interactions, and they are relatively frozen in the translational movement. Pharmaceutics is the way the drug product design is carried out, and what are the characteristics and the performance criteria for the drug product are studied in the course of pharmaceutics. So when we combine these two aspects, that is solid state and pharmaceutics, we are going to understand how the solid state behavior impacts the pharmaceutical behavior is going to be studied in this coursework of solid state pharmaceutics. Today we are going to have our introductory talk on these topics: introduction, molecular level, levels of solid state, crystalline state, intermolecular interactions in crystals, and PXRD or the X-ray diffraction, a key tool in solid state characterization. We will try to cover the first two or three topics today in this particular class. What is solid state pharmaceutics? The three different states of matter are gaseous, liquid, and solid state. In the solid state, the molecules are held together by intermolecular interactions, and there is a long range order existing in the material. In comparison to that, in the liquid state, there is only a short range order, which means some of the neighboring molecules are ordered with respect to each other, but rest of the molecules are in a disordered state. In comparison to that, in the gaseous state, all the molecules are in the state of disorder. Pharmaceutics is the discipline of pharmacy that deals with all facets of process of turning a new chemical entity or a active pharmaceutical ingredient into a finished dosage form, which is able to be safely and effectively used by the patient. In other words, pharmaceutics is the science of dosage form design. The field of science that links the solid state properties to the dosage form design is termed as solid state pharmaceutics. It is interesting to know that this coursework on solid state pharmaceutics, Naipur Mohali was the first one to start this coursework, and thereafter this coursework was started in some of the other universities as well. Why to study solid state pharmaceutics? A large number of pharmaceutical products are sold in the market in the solid dosage form. The examples include tablets, capsules, dry syrup, dry powder injections, dry powder inhalers, and powders for sprinkling. If we want to develop robust products in terms of stability and performance, it is necessary to characterize and control many properties, including the solid state properties of the active as well as the excipients in the dosage form. This is where the significance of this coursework lies, that it helps us in understanding what properties are important for the stability and performance of solid dosage forms like tablets, capsules, etc., and how they can impact their overall behavior. Solid state can be classified into three levels: molecular level, particulate level, and bulk level. Let us look at these levels one by one. Molecular level encompasses properties like crystalline and amorphous nature, arising out of the interaction between the individual molecules in the solid state. This area of study concerns with the molecular state of the drug in the solid state. There are two pictures that have been shown in this slide. The first picture shows the molecules are arranged in a highly ordered form. Such a form of the solid is called as the crystalline state. Here is another picture which shows some of the molecules are ordered in the short range, but the long range order is missing in these set of molecules. This state of solid state is called as the amorphous state. Obviously, we will be discussing the crystalline state and the amorphous state in much more detail in later classes. Particulate level concerns the properties of single particle. It deals with properties of individual particles and includes properties like particle size distribution or surface area of both the active drug and excipient, crystal habit, crystal shape, particle morphology, and surface characteristics like roughness, texture, porosity, and friability. The importance of particulate level can be easily understood by looking at the importance of particle size distribution in the dry powder inhalers. Here are two pictures of a polymorphic form of silicoxis which exists in two different crystal shapes. The first one are the plate-shaped crystals and the second one are the needle-shaped crystals. Both these crystals are of polymorphic form 3 for silicoxis, but they are different at the particle level. Again, we will be learning more about the particle level in our subsequent classes. Bulk level properties encompass an ensemble of the particles. Ensemble means a group of the particles, and it includes properties like bulk density, compressibility, flow, cohesivity, loose aggregation, and fuse agglomeration. It has main significance during processing of the solid dosage forms like granulation. In fact, during granulation, we deliberately change the bulk level of the powders by including a binder in the formulation so that the powder is converted into granules. So we have learned till now what is solid state pharmaceutics, and what are the three levels of solid state, that is the molecular level, particulate level, and the bulk level. These three levels of solid state in fact are interdependent on one another. What we mean by interdependence is the fact that if you make a change at one level of the solid state, it is going to be reflected as a change at the other level as well. Let us look at the changes at the molecular level. They are percolated to the particle level as well as the bulk level. For example, if you change the non-crystalline portion, polymorphic form or pseudo-polymorphic form of a material, there are going to be changes in the crystal habit, and changes in the crystal habit will reflect as changes in the bulk properties as well. Similarly, if you make the changes at the particle level by changing the particle size, particle shape, or porosity, you are likely to see some changes at the preceding level, that is the molecular level, as well as the proceeding level, that is the bulk level. This is called as the solid state pyramid, and this depicts interdependence of different levels of solid state on one another. We will now look at the significance of solid state properties in the life cycle of a solid dosage form. The conversion of a drug substance to a drug product, which is the dosage form, involves all the three levels of solid state, and it is important to control all these parameters to ensure predictable drug product performance. This diagram shows the journey of the API to a finished dosage form like a film coated tablet. Initially, we take the API and the excipient, and the first step in the tableting process is the dry blending step. Then the next step is wet mask if we are using a wet granulation process. And then we obtain a wet dough mask which is passed through a sieve to obtain granules. which are dried to obtain a dried granules, which are then sieved to obtain the right size of the granules for tableting. These granules are then lubricated and then they become ready for compression, and then they are compressed into the tablets which can be subsequently film coated. Now every step or the every unit process in this cycle involves the role of the solid state properties, and these boxes are depicting those solid state properties that are operational at the level of each unit process. We are going to look at couple of them so that we can understand the significance of the solid state properties during the processing and manufacturing of the solid dosage forms. At the stage of the dry mixing, amorphous form, polymorphic form, and pseudopolymorphic form of the API will have an implication because they will have different surface properties and different flow properties. Similarly, at the particle level, the particle size and particle size distribution will affect the mixing efficiency. As we all know, it is always easier to mix the larger particles as compared to the smaller particles. Shape of the particle will affect flow and mixing. Density differences between the API and the excipient will affect the mixing efficiency and their separation tendency as well. Similarly, if we pick up the stage of compression, we can look that during the compression stage, there is plastic deformation, fragmentation, hardness, thickness, disintegration, and dissolution taking place. And the solid state properties like polymorphic form, amorphous content will have a significant impact on the compressibility behavior of the powder. Similarly, during the film coating state, the friability of the tablet during coating, and there is a possibility of phase transformation on the tablet surface, and lamination and capping can take place during the coating, and these are all affected by the solid state properties. So the reason why we went through this particular slide was that we wanted to understand that how the solid state properties are affecting each unit process during the manufacturing and generation of the solid dosage forms from API and excipients. So the take-home message in terms of how the levels of solid state affect the product development is that it is important to know and control the solid state characteristics of the excipients and API in the dosage form as it affects processing, stability, and performance. We will now start with the broader or the deeper understanding of molecular level of the solid state. This is the classification of the molecular level of the solid state. Broadly, there are two classes within the molecular level, the crystalline and the amorphous form. The crystalline form could either be single component or multi-component. Within the single component, you can have anhydrous or non-solvated form and their polymorphic forms. Multi-component crystalline solids include hydrate, solvate, and their polymorphs, salt forms, and co-crystals. These can further exist in different ways, like hydrates, solvates, and their polymorphs could combine with the salts to give you hydrated, solvated salts and their polymorphs. Similarly, the salts could either be anhydrous, non-solvated, and their polymorphic forms, and there could be co-crystals of salts and their polymorphs, solvates, and hydrates. Co-crystals could also be anhydrous or non-solvated and their polymorphic forms. They could also be hydrated and solvated co-crystals and their polymorphic forms. On the other extreme, we have the amorphous form, which can either be single component or multi-component. Single component amorphous form could also be called as the anhydrous or the non-solvated amorphous form, while the multi-component can be hydrates, solvates, salts, and amorphized co-crystals. This is a classification system for the molecular level of the solid state. What are polymorphs? Organic molecules can crystallize as different solid forms, and this phenomena is called as the polymorphism. This hexagon depicts the organic molecule, and you can see that it can arrange in the supramolecular state in this way and in this way as well. This we will call as the form 1 crystalline form, while this is the crystalline form 2 of the same organic molecule. The organic molecule, which is the building block, is the same in both the cases. The only difference is that the molecules are arranged in different manner in these two polymorphic forms. There are also multi-component crystalline solids, wherein this hexagon, which is blue color, depicts the API. Green color box indicates the counter ion. Inverted triangle indicates water or the solvent. And this rectangular shape indicates the neutral gas molecule. We can have neutral species as well as charged species in the multi-component crystalline form. Under the neutral species, we can have polymorphs. Homomeric polymorphs are those wherein only the API molecules are involved in the phenomena of polymorphism. Hydrate and solvents involve both the API and the water or the solvent molecule in the crystalline arrangement. Co-crystals involve the API and the neutral gas molecule. Hydrated co-crystals involve the API, neutral gas, and water or the solvent molecule. In the charged entities, we have the salt forms, wherein you have the ionized API and the counter ion present in the crystalline state or in the crystal lattice. Salt hydrate additionally will have the water molecule in the crystal lattice. Salt co-crystal will have the charged API, the counter ion, and the neutral gas molecule. Salt co-crystal hydrate additionally will have the water or the solvent molecule as well. So this is the largest entity, you can say, because there are 4 types of species that are involved in formation of salt co-crystal hydrate. You have the blue colored API, you have the gray colored neutral gas molecule, this is the counter ion, and this is the molecule of water. Now we will move over to the crystalline state and try to understand in more detail what is involved in the crystalline state. Crystalline state is referred to the internal arrangement and outer appearance. When applied to solid, the adjective crystalline implies an ideal crystal in which the structural units termed as unit cells are repeated regularly and indefinitely in 3 dimensions in space, and they have a marked geometry, long range order, defined angles, and plane spaces. On the other hand, amorphous solids lack long range order. Obviously, we are going to look at these aspects in more detail in the subsequent slides. First term that we are going to look at is what is long range order that is present in the crystalline solid. This is also called as translational periodicity. Here we have shown a contingent of soldiers giving a march past on the Republic Day. What is interesting to see is that each soldier has the similar arrangement during the march past. Look at the way their legs are, their hands are, their head is, everything is in the same manner. This is called as the ordered arrangement or the long range order, where each soldier has a similar arrangement throughout the contingent. Similarly, in crystals, the molecules are arranged in regular rows or networks in the 3-dimensional lattices. A regular alternation of molecules separated by same distances is repeated for molecules separated by any distance. That is, there is both long range as well as short range order, and this happens due to interaction between the molecules by way of intermolecular interaction. However, a completely ordered state is only possible at absolute zero temperature, since the order is going to be disturbed by thermal motion. The building blocks of a crystal are also called as a unit cell. From a purely geometric point of view, that is ignoring the exact placement of the atoms or the molecules, each crystal can be explained by the smallest repeating translational unit in three-dimensional space called as the unit cell. Unit cell has a definite orientation and space and shape, and hence has a definite volume. Each unit cell is of same size and contains the same number of molecules or atoms arranged in the same way. It is convenient to think of atoms or molecules as point sources and the crystals as a three-dimensional array of these points. The array is called as the crystal lattice or the crystal system. An ideal crystal consists of structural unit termed as unit cells that are repeated regularly and indefinitely in the three-dimensional space. Unit cell is the smallest repeating translational unit in three dimensions, and it has a definite orientation, shape, and volume. A unit cell is a parallel pipe that can be described by six geometric measurements: the unit cell length A, B, and C, and the unit cell angles alpha, beta, and gamma. This is the depiction of a unit cell. So this is the smallest repeating unit that we have, and it is the unit cell of a given crystal lattice or a given crystal system. So these are the lengths A, B, and C, and the angles between them alpha, beta, and gamma. So these six parameters are used to define any unit cell arrangement. There are seven basic unit cell arrangements called as cubic, tetragonal, hexagonal, rhomboedric, orthorhombic, monoclinic, and triclinic. And in them, the six parameters that we studied are shown on this column. In the cubic, A is equal to B is equal to C, and alpha, beta, and gamma all are equal to 90 degrees. In tetragonal, A is equal to B, which is not equal to C, and alpha, beta, and gamma all are 90 degrees. Similarly, for hexagonal, rhomboedric, orthorhombic, monoclinic, and triclinic, the values of A, B, C, and alpha, beta, and gamma have been shown on this side. In drug molecules, only three common types of unit cells are observed, that is triclinic, monoclinic, and orthorhombic. Rest of the unit cells are seen in the case of inorganic crystals. Let us differentiate here that all the drug molecules are mostly organic in nature, and our emphasis during this class is going to be on organic crystals. There is a different and a separate field of inorganic crystals, for example, sodium chloride, potassium chloride crystals, magnesium chloride crystals. These are not going to be studied in this class. What we are going to study here are the molecular crystals. In the case of molecular crystals, the smallest unit that contributes to the formation of the crystal is a molecule. Whereas in the case of inorganic, it is going to be sometimes an atom or an ion. These unit cell arrangement with end-centered, body-centered, and space-centered arrangements are also possible, which in total gives us 14 Bravais lattices. These are shown here diagrammatically. We have simple cubic arrangement, space-centered cubic arrangement, body-centered cubic arrangement, simple tetragonal, body-centered tetragonal, and hexagonal. simple orthorhombic, body-centered orthorhombic, base-centered orthorhombic, face-centered orthorhombic. Similarly, you have rhomboedral, simple monoclinic, base-centered monoclinic, and triclinic arrangements. There are different components of a crystal apart from the unit cell, and they include space group, which is defined as any of the ways in which the orientation of the crystal can be changed without seeming to change the position of its atoms. These changes may involve displacement of whole structure along a crystallographic axis, that is a translational displacement, as well as the point group operations of rotation about an axis. Theoretically, there are 230 space groups are possible, but only a handful are observed in the case of molecular crystals. A combination of crystal systems, space group, and individual atomic coordinates defined each unique crystal structure. This is a molecule of celecoxib that has been shown, and this is a unit cell of celecoxib. You can see there are two molecules in one unit cell of celecoxib. This is the axis, this is the A axis, this is the B axis, and this blue colored is the C axis. We are going to stop here for this particular class, and in the next class we are going to study about the intermolecular interactions that exist in the crystalline form. Again, if you have any questions, you can post them in the WhatsApp group created for this particular coursework, or else we will also have dedicated classes to settle your questions. Thank you very much for your attention.